Hey there, and welcome to this lecture on control of microbial growth. This would be chapter 7 for my microbiology course. This will be a two-part lecture. It's a fairly short chapter on ways in which microbes and their growth can be controlled and the different techniques that we use to do that. So let's get started. So some terms that we want to look at, and by the way, there are a number of terms in this chapter, a lot of terminology and vocabulary related to this. So pretty easy chapter, straightforward, a lot of terms to keep straight. That's probably the most difficult part, but nothing too complex or too involved. So some terms, sepsis refers to microbial contamination, and asepsis, you put the prefix a in front of it, and now you're without microbial contamination or the absence of it. Aseptic surgery techniques prevent microbial contamination of wounds. This all began with Joseph Lister in the 19th century, where he started using carbolic acid, or what we call phenol, to prevent infection of wounds. What happened here, though, and I have this picture here as an example of what we would call today septic surgery in the Civil War, and it was awful. More men died of septic wounds than they did from bullets in the Civil War. And what I have here is a picture of a traveling physician, traveling doctor. That's his shop there, that covered wagon. And if this was the most common procedure that was done, amputation below the knee. And so what he would do would be to lop off the limb, usually the lower portion of the leg, clean knife by wiping it against the sole of your boot, and then amputate the next limb. So the doctor is the gentleman who's obviously doing the work here. He's holding the man's ankle and cutting off his leg below the knee, and his assistant would use some kind of anesthetic ether of some sort, put wooden rods in their mouths to bite down on because the pain was so excruciating. You often hoped, as the I guess you could say the patient, or what you might call the victim, that you would pass out from the excruciating pain of procedures like this. Um, the doctor here, he wrote a journal, and he journaled his work in the Civil War, and you can actually read it online, his actual handwriting in a journal. And these are basically what he said. You would have the knife, you'd have the tissue on it from the person you just amputated, and then the next person would come along, the next soldier. You would literally just wipe the saw or the knife against the sole of your boot, or a leather apron that they would wear, or your coat, and then move on to the next person. And so much disease was transmitted this way, so many bacteria from one soldier to the next. And so sepsis was just rampant among these poor individuals. This, of course, was before the germ theory could take hold. It was even then it was in its infancy, during the Civil War times. In Europe, in the United States, it really wasn't. They hadn't really caught on much at all, and the Civil War distracted us from making any kind of advances in terms of aseptic surgical techniques and the germ theory of disease. So this was a real problem during this time period in the United States. But after that, advances started to be made, and in the late 19th century, we had a fairly good idea about proper surgical techniques, but we still had a long way to go even then. A few other terms: sterilization, removal of all microbial life, usually by heat, so that's typically the way that it's done, high temperature. Commercial sterilization, killing Clostridium botulinum endospores in canned foods by heat. So it's a regulated temperature that has to be met in the canned food industry in order to kill these endospores. And the Clostridium botulinum endospore produces a deadly toxin, very deadly toxin. That this bacterium is found in the soil and can get transmitted from the soil onto, say, vegetables, for example, green beans or something like that. And so when they're harvested and then they're canned, the temperature of these canned foods has to reach a certain level in order to be deemed safe. They're not. It's at a temperature that doesn't kill everything, but it's at a temperature that kills these deadly endospores of Clostridium botulinum. Disinfection, so removal of pathogens using chemicals that we call disinfectants. We can use ultraviolet radiation, boiling water or steam will disinfect, so it's removing them from a surface or from, say, a water supply, for example. You might have a UV system in your house to disinfect the water as it comes into your home. Antisepsis, removal of pathogens from living tissue, and we call them antiseptics. So disinfectants typically on inanimate surfaces or using them not on a person or on an animal, for example, as a vet would use an antiseptic. Antiseptics then are on living tissue. They're utilized on living tissue to remove pathogens. Degerming is a process of removal but not killing microbes from a limited area, like cleaning an injection site, for example, like you see in that picture there. That would be degerming, using a chemical compound of some sort. In this case, it looks iodine or betadine, so that you're removing them from just a small limited area. Sanitization is the process of lowering microbial counts to reduce disease transmission among a large group of people, for example, or like within the agriculture, a herd of milk cows, for example, a herd of heifers. For example, on restaurant eating utensils as well. So there are guidelines that are set, temperature that has to be reached in order to be considered safe and I guess legal. So those temperatures must be met, and they're regulated by government agencies, making sure that these diseases, these microbes do not get transmitted in a population. A biocide or a germicide, they kill microbes, but they're not capable of killing endospores. Endospores are really tough to kill, especially using some kind of a chemical compound, because they can't penetrate the thick, unusual cell wall that the endospores will form around themselves. And so the endospores actually can survive a number of chemical compounds that we would classify as a biocide or a germicide. So these are killing agents, killing chemicals, but not capable usually of killing endospores. Bacteriostasis means inhibiting but not killing microbes. So say, for example, refrigeration. Refrigeration carries out bacteriostasis, where the numbers remain static or stasis, and that's what that suffix refers to, remaining the same and not increasing in number. So you put your foods in the refrigerator, yes, they have bacteria on them, but the bacteria aren't reproducing because the temperature is so low, they can't metabolically carry out that process, and so their numbers remain static or level. So how effective an antimicrobial treatment is depends on a few factors. The number of microbes, common sense, the more there are to begin with, the longer it's going to take to kill them. Environmental factors, like what's on the surface, organic matter that could interfere with the effectiveness of the antimicrobial. So there are factors that could render it useless, for example. Temperature, biofilms, which are thick conglomerations of microbes that are growing together that we'll talk about in a later chapter. Biofilms are very resistant. They're very problematic to deal with. Pathogenic biofilms are. There are plenty of biofilms that are very beneficial to us, especially out in the environment and in the ecosystems. Time of exposure to the antimicrobial, so there's a certain length of time that the antimicrobial should sit on a surface in order for it to be effective. And the characteristics of the microbes themselves, like if you're dealing with bacteria, they're gram-positive or gram-negative. What's the resistance factor of these microbes? So these are four big factors that can affect the antimicrobial effectiveness. How do they kill microbes? And I've mentioned this before. The number one target is the plasma membrane. So if the plasma membrane can be breached, then the microbe is going to die. Especially in terms of bacteria, if you can take down their cell wall outside of the plasma membrane, that too is a way that will lead to the death of the bacteria. So if the peptidoglycan can be taken apart, then they cannot resist osmotic pressure, and the plasma membrane will burst as a result of that. Damage to proteins, like denaturing enzymes, so tearing enzymes apart, or using inhibitors of enzymes. Competitive and or non-competitive inhibitors can be utilized to disrupt the enzymes, prevent them from functioning so that they can't carry out their vital processes within the bacterial cells, for example. Damage to DNA and or RNA by heat, radiation, or chemicals, so destroy the nucleic acids. Now you destroy protein synthesis and the ability for the microbes to reproduce as well. So these are targets that we utilize. So we go after the membrane, or in the case of bacteria, the cell wall also, destroying or disrupting their enzymes, and also the third target, the nucleic acids, preventing them from reproducing and multiplying and producing proteins. So we're going to look at physical and chemical methods to control their growth. We'll look at physical first and then move on to chemical methods. So heat is the number one way, the number one physical method to control microbial growth. And the reason why, it denatures enzymes. So target the enzymes, shut down the enzymes, cause them to denature, unravel, and fall apart. They can't carry out their vital biochemical processes, and so it's done. Now, some terms that I wanted to introduce to you related to heat are these ones: thermal death point, thermal death time, and decimal reduction time. So I'll explain them a bit, and then I want you to see something that's similar among them. Lowest temperature at which all cells in a culture are killed in 10 minutes. So they want to achieve the lowest temperature to kill all cells in 10 minutes. Thermal death time is the minimal length of time required to kill all cells in a culture. And the decimal reduction time, minutes to kill 90% of a population at a given temperature, used in the canning industry. So especially with the first two, thermal death point and thermal death time, I want you to notice the terms that are used: the lowest temperature, minimal length of time. So these are regulated temperatures. These are regulated criteria that need to be met in industry, in the food industry, for example, so that the food can be deemed safe. And what industry is wanting is, they're looking at bottom line. So how can we make our products safe and yet not have to spend so much money on making it safe and meeting the regulations that have been set? So we, microbiologists and biologists and all kinds of other ologists, work together to determine, well, what temperature would be the lowest to kill all cells in a culture in 10 minutes, or what's the minimal length of time to kill the cells in a culture? And then those times and those temperatures are then applied to industry. And industry is looking for the lowest and the minimal length of time, because the higher the temperature, the more the expense. The more time exposed to a particular temperature, the greater the expense for the industry. And so these are this is kind of like the marriage of making something safe, but also making it cost effective as well for industry. The decimal reduction time, that's when 90% of a population is killed of bacteria, whether they're pathogenic or not. But we're dealing obviously with pathogenic bacteria. When 90% are killed, that's deemed safe. That 10% of the population is not a great enough amount in order to cause disease within people. And so this is the number that has been set. So if 90% of the pathogens are killed, if 90% of their toxins are neutralized, then it's deemed to be safe. And it's used extensively often in the canning industry. Moist heat would be, well, we got water, boiling, or using the autoclave, which is extremely effective. Steam under pressure, 121 degrees Celsius, that's about 250 Fahrenheit, for 15 minutes at 15 pounds per square inch pressure. So this is heat or steam under pressure. And what that does is it denatures proteins, which of course would be denaturing enzymes as well. So boiling is effective. Autoclaving is much more effective, because you can get the temperature. With boiling, you're stuck at 100 degrees Celsius or 212 Fahrenheit. With autoclave, the temperature can be raised because it's under pressure. And so an autoclave itself is a pretty well-built machine because it's under pressure. So you put your surgical instruments, or in the case of a micro lab, you put your auger in there or whatever you want to sterilize in the autoclave. The whole process takes approximately 45 minutes from start to finish, thereabouts. But for 15 minutes minimum, and on most autoclaves you can adjust this, that will ensure sterilization. So once the autoclave gets up to 121 Celsius and 15 psi, it will keep it there for at least 15 minutes. And that is the time and temperature and pressure at which sterilization can be achieved. Pasteurization, named after the rock star Louis Pasteur himself, that reduces spoilage organisms and pathogens. And I wanted to look at equivalent treatments for milk because we talk about pasteurization so often, but you can essentially pasteurize anything. It's just applying temperature for a certain amount of time, applying heat. But we use it in the dairy industry most commonly. So when we say pasteurization, we often think of milk. The original treatment was 145 degrees Fahrenheit for 30 minutes. So that was maintaining a pretty high temperature for a long period of time. And it was found that that was creating a lot of cost to keep a large quantity of milk at such a high temperature for such a long period of time. Today's method is called the high temperature short time. So increase the temperature, just 16 degrees, and reduce it from 30 minutes to 15 seconds. And that's today's method that would be used in a dairy, for example. So rather than heating up a large volume of milk for a long period of time, it was determined that it would be much easier to take the milk and squeeze it through in the dairy processing within the dairy itself, squeezing it through thin films of, say, stainless steel, and having not such a large volume of milk having to be pasteurized for such a long period of time. So reduce the volume, increase the surface area of the instrumentation, the machinery that the milk is traveling through, and you can reduce the time way down because the volume has gone down so much. Kind of think of it like the radiator in a car's engine. Unless you have a Tesla and you don't have one. But in a gas-powered engine, the radiator takes the coolant and pushes it through the thin films of metal, and then as a result that increases the surface area, and you don't have all the antifreeze just in one place, and so it can cool down rather quickly. Ultra high temperature, or UHT, jacks the temperature up to 284 degrees for about 2 seconds. This achieves full sterilization. Now, our method, the high temperature short time, the one that's used most commonly, that does not achieve sterilization, but it's a temperature. It's at a temperature and for the length of time that it's administered is sufficient enough to kill pathogenic bacteria that may be in the milk. And you don't know. I mean, the milk could be perfectly fine. There might not be any pathogens in it whatsoever, but we don't want to take the chances whenever we're processing such a huge volume of milk from dairy cows. But again, back to UHT, that achieves sterilization, which means no refrigeration is required. It's important in areas where refrigeration is impossible. It's used for many dairy products like half and half, creamers and coffee, for example. There's UHT milk as well. None of this milk needs to be refrigerated. None of these milk products do. You look at other ones, heavy whipping cream, for example, is UHT. Why we put it in a fridge? I guess it's just for our comfort, for the traditional, psychological. I don't know, if people saw milk sitting out on shelves at room temperature, we might, oh, that milk is spoiled. But if you go to Europe, where almost all of their dairy products are treated UHT, they're all just sitting out on shelves. You can Google image like a grocery store or dairy products in Europe, and you will see pictures of it sitting out on shelves rather than in refrigerators. Now, why do I make this point? Well, it's expensive. I mean, we're refrigerating, if you think about it, across this country, millions of gallons of dairy products unnecessarily. And so you do the math and figure out how much is that costing, how much space is it taking to refrigerate, how much cost is it requiring to keep these products refrigerated and keep them at a low temperature when they don't have to be. They're totally sterile. They can be sitting out on shelves and it would be fine. And next time you go to the grocery store, check it out. There's different brands of milk that uses UHT. Nearly all half and half, nearly all heavy whipping cream is all sterilized at UHT temperatures. They could be moved out of the fridge and put onto the shelves. I think that could save quite a bit of money, but what do I know? So anyway, that's used in many products, and we have seen that too. I'm sorry, I'm going to say one more thing. Where you see like those creamers called moo-moos, for example, they're just sitting out. Many times, if you go to a cafe or something, they're just sitting on the table. It's half and half. It's dairy, but it's sitting out at room temperature. They're not taking it out of the fridge and giving it to you. They're actually just letting it sit there all day on the table, for example, because it's sterile. Now, when you open it, of course, then you've lost sterility. It's no longer sterile. But until it's opened, it will remain sterile. Some bacteria do survive pasteurization, like I said, but they normally don't cause disease, so they're fine. We consume plenty of bacteria when we drink milk that uses today's method, but they're non-pathogenic. There's dry heat sterilization, like flaming and inoculating loop, for example, in a microbiology lab. You can incinerate things, which is a special process that just churns the waste over and over again until its volume is reduced in a great amount. So incinerating garbage, for example, in the United States, we're not big into incineration. We don't need it because our land is so vast. But in European countries where land is limited, they have large incineration facilities that reduce the volume of their garbage by over 80%. Hot air sterilization in an oven. And so I have equivalent treatments here, and I meant to say that on the last slide. Equivalent treatment, they are treatments that achieve the same thing, in this case sterility. So if you use just plain hot air, 340 degrees for 2 hours in an oven, say, for example. An autoclave will achieve the same thing at 250 degrees Fahrenheit for 15 minutes. So you can see the difference between the two. Less temperature for autoclave and a much shorter time as well. By the way, what I was saying about incineration, this is an incineration plant in Europe. It's in Sweden, I think is where I got that picture from. This is not incineration, a burn barrel. Some of you who are from some rural areas, you might have a burning barrel. It looks like this one didn't go too well, though. The bank behind it looks like it's been incinerated. Whoops. So anyway, what these facilities do is they, like I said, they burn the garbage, they churn it, it just keeps cycling around and around and around to reduce the volume of the garbage. Here in the United States, we just typically use landfills. We don't do anything with it. We just put it in a garbage truck, it gets compressed, and then it gets put into a landfill where it decomposes, but some of our garbage, of course, doesn't break down. And so we just fill up the land with our junk. But anyway, like I said, land here is plentiful, and so we're not really interested in building these multi-million-dollar facilities. At least we don't need to right now anyway. Other physical methods of control is filtration, like using a HEPA filter, for example, that filters the air, say in an air conditioning system or a heating system. Low temperature will inhibit microbial growth. It's like bacteriostasis, where refrigeration will slow metabolism. They don't produce toxins. Deep freezing does. Ice crystals will destroy the structure of the microbes. Freeze drying removes all water, so there's no water available for their metabolism. And so these products can be kept at room temperature because there's no water in there to carry out any biological processes with freeze drying. High pressure will denature proteins, like, of course, enzymes, so squashing them and tearing apart the three-dimensional structure of the enzymes. Desiccation, totally drying out, so no water available, no metabolism, but doesn't kill them, but eventually they're going to die out because there's no water available. Osmotic pressure will cause plasmolysis. That usually refers to salting or having a lot of sugar, like, for example, in a syrup. Corn syrup, it just doesn't go bad. Honey doesn't go bad because of the plasmolysis that occurs in the microbes if they land on it. You don't need to refrigerate your syrup. I've been to places where I've seen pancake syrup, for example, put in a fridge. You don't need to because anything that gets on it, it'll plasmolyze. Water will osmose out of any bacterial cell and it's done. Radiation damages DNA and RNA. Microwaves kill by heat, so microwave radiation, it's not antimicrobial, it just raises the temperature to the point where it can kill bacteria, so the microwaves aren't actually killing them. Microwaves are low, in comparison to other forms of radiation, microwaves are low energy. And they microwaves are, for example, like um, if you look at a microwave, it's not like it's a vault that prevents the microwaves from getting out. You can stand next to a microwave, it's okay. You're not going to irradiate yourself. They just raise the temperature, and as a result of that, that can lead to death of bacteria. But at a higher energy level radiation, that will tear apart nucleic acids, like ultraviolet radiation, for example, will tear apart DNA and cause obvious problems in skin cells, for example. Chemical methods of microbial growth. So we want to, what are we looking at here in terms of chemical methods? So this is back to where I was saying about effective disinfection. So, and we're going to look at the chemicals that can affect it. The concentration of the disinfectant, how much can it be watered down? Could it be too much and cause problems, like on skin, for example? Could it cause a chemical burn or irritate respiratory passages or something like that? Consider the surface that's being disinfected as well. Will the disinfectant make contact with the microbes or just the dirt on the surface? So clean up any debris first and then spray on the disinfectant. The pH can affect the disinfectant as well. pH of the surface being sprayed can neutralize these chemical compounds because we're dealing with chemicals here. So pH is a chemical factor, and so that can alter the disinfectant's ability to disinfect because of the chemical interactions. Length of time it's on the surface as well, so this is obviously a factor as well. So this is kind of a repeat of a slide that I mentioned earlier, but I want to look at it with more of a chemical focus. How are disinfectants tested? Well, there's one way. It's called the use dilution test. Like, how good is the disinfectant, or what solution can it be produced at and then sold? Well, take metal rings, dip them in test bacteria, and then the metal rings are dried. These dried cultures, which are on the rings, are placed in the disinfectant for 10 minutes at room temperature because they want to try to mimic, I guess, actual environment in a home, for example. And then the rings are transferred to culture media and to see if the bacteria survive the treatment or not. If nothing grows, then the disinfectant was effective. If bacteria do grow, well, then something was wrong. It wasn't effective for some reason because of the dilution or whatever. So this is one way that disinfectants are tested. How do they work, and how do we need to produce them? Another way is the disc diffusion method, where you take simply just take a paper disc and dip it into a disinfectant, and then place the paper discs on Petri plates that are covered in bacteria, and then incubate them. Then, after 24 hours, take them out of the incubator, and this is what you'll see. And where the paper discs are, that's where you're going to be looking for what's called a zone of inhibition. In the upper left there, you see that. And you can see how these different disinfectants, how effective they are against different bacterial species. There's Staph aureus on the left, E. coli in the middle, and Pseudomonas aeruginosa on the right. Now they're using all the same disinfectants, and you can see how they perform against different types of bacteria. Like, for example, hexachlorophene works really well against Staph aureus, but it does nothing against E. coli or Pseudomonas, and mainly because those two species are gram-negative, whereas Staph aureus is gram-positive. So the larger the zone of inhibition, the more effective that disinfectant is against a particular species of bacteria. It's a very easy test. It's very visual. You can see what's going on, and it's useful. And it's a pretty quick preliminary test to determine the effectiveness of a disinfectant. Okay, that's the end of part one. Part two will be quite a bit shorter, but I wanted to cover up to chemical methods of microbial control. So stay tuned for part two, and thank you for watching.